So we're going to start our discussion of counting with something that's relatively simple. But this is one of those things that it's helpful to think through and really kind of quantify because while it's not particularly complicated in its own right, it's one of those things that's going to be a useful tool for us as we get further into this. So what we want to do here is we want to count the number of elements on the list. All right, so here we have a list of integers from 2 to 7, and I want to know how many integers are on it. Okay, well, the first thing we need to be clear about is when we talk about something, a list from a number to a number, we're including the two numbers at the end. Right, so we want to include 2 and 7 in our count here. Now, the natural thing to do is to just subtract the two numbers and say, okay, well, it's 7 minus 2, but if you do that, it doesn't work. Right? If you do that, you get 5, and 5 is not the answer. Right? And here's why. Subtraction really doesn't do what we need it to do. And I've got a number line here. We kind of flash all the way back to the first grade and how you first learned about subtraction. To do 7 to 2, I'm going to start at 7, and I'm going to count backwards until I get to 2. Right? So I'm going to go 1, 2, 3, 4, and 5. And yeah, okay, we did come up with 5. But what does that 5 mean? Right? Well, what we did here is we counted the steps from 7 back to 2. So that counted this one, this one, this one, this one, and this one. And now hopefully you can see the problem. Right? This idea of counting the steps that we mean when we talk about subtraction doesn't include the initial number. And we want to include the initial number, right? We want to include both 2 and 7. So there's a really simple fix, or a really simple correction to this, and that's just to add 1. And if we do that, we get 7 minus 2 is 5, plus 1 is 6. And if you actually count them up, because the list is fairly small, there are 1, 2, 3, 4, 5, 6 numbers. So that works. Right? So on the next slide here, I've made that explicit. Right? If we have two integers, m and n, where m is the smaller of the two, although we're allowing the possibility that they could be equal, then there are this many integers from m to n inclusive, right? Inclusive meaning we count m and n, the endpoints in the list, right? You see how this matches what we did in my numeric example, right? We had 7 minus 2 plus the 1. And that gave us the final result. You can confirm, right, in the case where m and n are equal, right? In other words, we have a list that only has one element, for example, just this one, right? Well, n and m are the same, so the formula in this case says we should have 5 minus 5 plus 1, which is one element. Yeah, okay, excellent. It works, right? Even in that special case, our formula is still doing what we would expect it to do. So I've got kind of an example here, right? Thinking from the computer science side, if we have an array, right? And an array is an indexed list of values. For example, we might have a of 1 equals 2, a2 equals 5, a3 equals 12, and so on. And we really don't care about what the values are, the 2, 5, and 12, right? What we care about is the array itself. So the question here, and we're going to kind of look at this as a way of both applying the formula that we just came up with and confirming that, again, that it's doing what we expect it to do, right? I'm going to take this array and I'm going to split it in two parts somewhere in the middle, right? So we have the values from 1 to m here and the values from m plus 1 up to n over here in the second sublist, right? So what I want to do is I want to use my formula to figure out how many elements are in each of these sublists, right? Well, looking at the left-hand one, it's pretty obvious with this one that there should be m, right? Because we just count from 1 straight up to m. So what does our formula say? Well, our formula says you take the highest index, subtract the lowest index, and add 1. And if you do that, you get m. Excellent. Exactly the result we expected to get. The formula is working. All right, now how about on the other side? How about for the upper half, the upper sublist? Well, let's apply our formula. The formula says we take the upper bound minus the lower bound and add 1. All right, so let's simplify this. This is n minus m minus 1 plus 1, which is n minus m. All right, that's a not unreasonable result, although I am a little suspicious because it feels like I'm just subtracting, and as we saw on the last slide, pure subtraction doesn't work. Now, granted, the starting index here is m plus 1, not m, but still, I'd like to do something to help me confirm that this is right. Okay, and here's how we can do that. Right, I know that these two sublists put together make up the whole list. So if I add the size of this list plus the size of this list, I should get n, right? Because I should get everything. I should get the original list. And that is what happens. If we do m plus n minus m, yeah, it does come out to n, which is the size of the list that we started with. So good. Our formula does seem to be working, right? In the sense that it's giving us what we expect from the situations where we already know what the result really kind of should be. All right, not a very complicated example to start off with, but like I said, it is going to be a useful one as we go down the road here, right? It is going to be helpful to have that formula in our back pocket. So in the next lecture, we're going to take just kind of the next step, and we're going to look at a more complicated counting example that's going to be more representative of the sorts of things that we're going to be talking about throughout the rest of this chapter.